So let's make a very quick video here covering some doubts and clarifying some things. So let's take a look at those examples here. So for each of the following functions, discuss the behavior near the asymptotes and hence deduce their equations. So we have this first function here, 1 over x. If you remember the graph of this function, if you don't, you should, but this is what we call a reciprocal function, right? So it keeps going here and there, and it never touches here, it never touches the vertical, and it never touches the horizontal axis. So that's the function that we have. Now, discuss the behavior near the asymptotes. So when, let's say, when x, so we have one asymptote here. What happens when x is approaching from the right? So when x is going to 0 from the positive side, what is going to happen? Well, f of x is going to approach positive infinity. What about when x approaches the same point 0, but now from the left, so from the negatives? Well, f of x will not go towards positive infinity, it will go towards negative infinity. Right? This function keeps going down. Now what about the extremes? What happens when x is taken to positive infinity? So f of x will approach 0. In this case, it's a positive 0. It's a number close to 0, but very, very small, but positive. And if we go towards negative infinity, we would have 0 as well, right? So since those values converge, right, no, because they're not the same point. If those limits here, if we had points going towards the same point and both limits were the same, then it would be converging, but here one is going positive infinity, the other one's going towards negative infinity. So we have here investigated the behavior near the asymptotes. Now what about the limits? So if I take the limit x towards negative infinity of f of x, it's going simply to be our asymptote. So when we go towards negative infinity, that's 0. And here you don't have to put signs. Now what about the limit when x is taken to positive infinity? It's also 0. And you don't have to express plus or minus here. So the next case here, we've got function of x, 3x minus 2, x plus 3. This is similar to the function that I showed you before, right? So limit x going towards negative infinity of 3x minus 2 and x plus 3. Now again, for us to work with this number, we're going to slightly modify this function. So if f of x is 3x minus 2 over x plus 3, okay, so let's try to get x plus 3 here on top. But since my x is multiplied by 3, I would need 3x plus 9. Remember, I'm trying to get some term which will cancel out with what I had down there. If I have added 9, I have to subtract 9 to get the same thing. So here on top, if you notice, I have not changed anything. 3x plus 9 minus 9, negative 2. I could cancel out those 9's, right? And I would just get back to what I had before. And now I can split this into two separate fractions. So this can be written as a subtraction of two fractions. So if I keep 3x plus 9 here up front, plus, and I'll just keep the negatives for now, okay? Minus 9 minus 2 over x plus 3, okay? So my function can be rewritten. Now I can factorize here by 3, So that's 3x plus 3 over x plus 3 minus, and negative 9, negative 2, that's negative 11 over x plus 3. That's minus 11 over x plus 3. And, well, here we can cancel those out, right? If x is different than negative 3, we could cancel those out, and then we would have 3 minus 11 over x plus 3. So if I'm taking the limit of my function f of x as x approaches negative infinity, this would be the limit when x approaches negative infinity of 3 minus 11 over x plus 3. Now, if I subtract two numbers in a limit, I can just split those. So I can write this as limit when x goes towards negative infinity of 3 minus limit when x goes towards negative infinity of 11 over x plus 3. Now, this is a constant, this is not. What happens when x increases? It's negative, yeah, but it's a huge number. What's going to happen with the denominator? This will go towards infinity. Therefore, the whole number will go towards 0. And, well, this is a constant, so I can approach any number. This will still be a constant. So this would be simply 3. And that is our horizontal asymptote, isn't it? If I take the limit now, x going towards positive infinity, what would I have then? Well, everything is going to be the same. Do you see that? Everything is, all the maths that we've done is going to be the same. And basically it's going to be 3 as well. Right? And that's it. So this gives you your horizontal asymptotes. If you remember, we have assumed that x was different than negative 3, right? Just because if it's equal to this, then this would be 0. So our function would explode, it would diverge when x is negative 3. Therefore, this is our vertical asymptote. That shouldn't be new. So, the only thing that should be new here is the limits part. Everything else, like asymptotes, you should know how to find those. But if you don't remember how to, there you go. That's another way of doing it. Now let's go for the last example here. So let's take the limit when x is going towards positive infinity, 1 minus 2x over 3x plus 2. Alright, and the last example here. I've got a technique that I use, and I'll show you. Okay, so when we look at those numbers and it's not really easy, we would have like fractions to try and simplify those. What I do is I get all of this underneath to be another variable. I'm calling it u, okay? Variable u. So 3x plus 2. If u is 3x plus 2, what is x in terms of u? Just rearrange it, right? You make x your subject. So x would be u minus 2 divided by 3, which is u over 3 minus 2/3. So we're going to put u here. So we're going to make this limit now in terms of u, and then we will move back to x again. But the thing is, if x is going towards infinity, take a look at x here. If x goes towards infinity, what's going to happen to u? U will also grow indefinitely. U will also go to infinity. So if we assume that x is going to infinity, it's the same thing as u is also going to infinity. So I could have limit of u going to positive infinity of 1 minus, and now 2 times x, just this, u over 3 minus 2/3 over 3x plus 2, which is u. So it's quite clear now that we're going to get something much, much simpler. Take a look. So limit, when u goes towards positive infinity, of 1 minus, now everything here is inside of the limit, 1 minus, and now we just expand this, so 2u over 3, and plus, because it's negative with negative, 4/3. All of this divided by u. Right, so I can get the constants together. So limit of u going towards positive infinity. So 1 plus 4/3, that would be 7/3 plus, minus 2u over 3, and all of this divided by u. Now let's split this into two different limits, right? So limit u going towards positive infinity. Now 7/3 is a constant, right? But I've got the u dividing here. So it's 7/3 divided by u plus limit u going towards positive infinity. I've got negative 2u over 3 divided by u. So I can get rid of those. And we can see that this is going to be a constant. This is going towards infinity, so u here is going to grow, and this number divided by divided by infinity will go towards 0. And this is going to be a constant, which is negative 2/3. Now, if you observe, everything that we have done would be the same for the limit if we take u going towards negative infinity, right? And remember, u going towards negative infinity will be the same thing as x going towards negative infinity. Because if you have infinity, or twice infinity, or 1/3 of infinity, it's still infinity. If you have infinity plus 1 plus 10 plus 100, it's still infinity. 100 is nothing compared to infinity, because infinity is something as large as you want it to be. So anyway, the limit going towards the negative infinity would also be negative 2/3. Everything works. If you compare the values, if you compare everything, we have done nothing that would be specific here for positive infinity. So negative infinity would also work. And well, so those would be your horizontal asymptotes. Your vertical asymptotes, those are easy. You just need to find when this is 0. When will 3x plus 2 be 0? Well, x will have to be negative 2/3. Now, the point here is when we approach from one side, we will have the function approaching 1 infinity. So if we're approaching from the left, take a look. If we take this value, if we take a number which is less than this, would it be negative or positive, the overall, the function? Well, if my number is, let's say, negative 1, which is larger, it's negative and larger than this would be a negative value. So I am covering negative values and going towards negative infinity. When I go to the other side of my function, then I would have positive values. So our graph would look roughly like this. So it's like that. Right? Not the best line. Oh, the best curve. Right? And we'll have another one like that. You can see that this is in the shape of 1 over x, but it has been moved. And if you remember your transformation geometry, well, it helps you a lot, right? Because 1 over x, you can get anything similar to it like those functions, just by moving them around, by moving on the x-axis, on the y-axis. So if you remember those transformations, x plus a or f of x plus a, it would help you a lot. You would solve this problem with much less effort. But well, I'm doing this working out in a more calculus focused way. So I'm doing some maths that I would expect you to be aware and good at. Now just to finish this, we would draw our, right, pretend that those are nice lines, right? So this one would be y equals negative 2/3, and this one here would be x equals negative 2/3. And the whole point here is, if you analyze, just as I was telling you before, if you approach negative 2/3 from the right, your function is positive. If you approach negative 2/3 from the left, your function will be negative. So that's why it diverges here. So there is no limit when x approaches this value here. Because from one side we have one value, and from the other side we have another value. Sometimes we have functions which are easier for us to see that they don't work. Functions with discontinuities, that we can see the discontinuities. For example, a function goes up to here, then there's no point here, and then it continues from down here up to another point, and then it's roughly flat. So this kind of function here, for example, there are discontinuities. So if I approach this value from the right, I'll get one value. But if I approach from the left, I'll get another one. So the limits would also not exist in this occasion.